Okay, so we've looked at some interesting restoring forces in this series. I want to show you now one of my favorites that leads you into a chaotic system. And I have a series coming up soon about classical chaos. So if you've enjoyed this series, if you enjoyed this video, make sure you check out the classical chaos series that'll be coming out on this channel shortly after this video goes up. What I want to look at today is a problem called the van der Pol oscillator. Right, we've looked at several oscillators so far. We looked at the spring, we looked at the superspring, we looked at the Lennard-Jones potential, we looked at the pendulum, we looked at damping and driving and all that stuff you can add on to it. What we want to do with the van der Pol oscillator is kind of similar to what we've done before. We've got an acceleration. We're not going to worry about calling it the force because it's just the force divided by the mass, so we'll just make the mass equal to 1 just for ease. What you do is you have two terms on the right-hand side. You have a damping term, and you have a restoring term. Let me show you what these are. The damping term looks pretty great. It's got a mu, that's going to be your damping coefficient, times 1 minus x squared. What that means is your damping is going to get worse the closer you get to the center. The closer you get to equilibrium, the worse the damping is going to be. If you get farther away, if you get close to x equals 1, you actually don't get anything from this damping term. And then if you get farther away from that, it gets worse again in the opposite direction. The important thing here is that there's going to be some special zone where you don't have any damping. So just keep in mind there's going to be a special zone somewhere along the video. Then we multiply that by the velocity because it is a damping term. So the faster you go, the worse the damping is going to be. Again, it's directional based on the v. So if v is positive, it goes one way. If v is negative, it goes the other way. Then you have a restoring term, minus x. Right? So this is exactly what you saw in simple harmonic motion. So if you take mu equal to 0, you should get right back to simple harmonic motion. Because if you cover up this piece here, you've got acceleration equals negative x. So you have second derivative equals negative of the function. To get you back to sine and cosine, not a problem. Before we go to the code, I want to get a general idea of how this oscillator is going to behave. So we're going to take a look at the phase space plot. All right, so phase space is very interested in looking at the two dependent variables, your position and your velocity. So you graph your velocity versus your position. And you always consider some kind of special case first. So let's consider the center point. Let's consider equilibrium of x equals 0, v equals 0. Well, if I put in x equals 0, there's no restoring force. If I put in v equals 0, there's no damping force. So at x equals 0, v equals 0, you get 0 acceleration. Right? Makes sense. That's the equilibrium point. You should be able to place the thing at equilibrium and have it remain. But the question is always, is this a stable equilibrium or an unstable equilibrium? Stable versus unstable equilibrium means if I move it away from equilibrium, is it going to fall back into equilibrium or is it going to fly away towards something else? Let's take a look. Let's suppose, for example, that I want to get to equilibrium, but I'm a little bit off in the x direction, right? So I'm at x equals a small number. Right? Let's take a look at what happens over here. So we'll have a small number over here. We'll have a small number in here, but it's getting squared. Right? And when you square a small number, it becomes even smaller. But actually, I don't even have to worry about this term because I'm still, let's suppose I can manage to get this thing at rest at v equals 0. So I won't have any damping term. I'll just have a equals negative x. What that means is I will have a negative acceleration. When I have a negative acceleration, it means my velocity is going to decrease. So in the first little time step, this point's going to jump down into this point down here because I'm going to have a negative velocity. I'm going to pick up a negative velocity. And actually, because I'm going to have a negative velocity, that means I'm going to move to the left on the x-axis a little bit. And so we're going to come over to here. So now we're at a point where x is positive and v is a negative number. Okay, let's take a look at what that means over here. Mu you're always going to have as a positive number. So I got 1 minus a small number, basically going to be 1, times a negative number. Right? So I have a negative and another negative. That makes it really negative, right? So my velocity is going to decrease even more. because my acceleration is going to be an even bigger negative value than I had up here. So here a is equal to a little negative. Here a is equal to a big negative, right? And so I'll end up going over this way. I'm going to jump even farther. So I'm not heading back toward equilibrium anytime soon, right? Because I'm ending up jumping farther away. Now, eventually what will happen, I'll end up in this quadrant, right? And so over here, I've got x as a negative and v as a negative. So I'll have a negative over here competing with a negative over here. So I'll have a little bit of a restoring force, meaning my acceleration is still going to be negative, but it won't be quite as negative. So now I'm going to start to slow down. Right? So you work this out. Eventually, this thing slows down until I reach some special set of points out here where it ends up being stable. So there's going to be some kind of curve out here where my motion is stable. It's not at rest, right? The only place I can stay at rest is if I exactly get the equilibrium point here. But I do have, maybe call it an equilibrium ring out here somewhere. The technical term for this is a limit cycle. It's a cycle in that it repeats, and it's a limit in the sense that it's what you approach as time goes on toward infinity, right? So I'm eventually going to fall into a limit cycle here that I'm going to keep going around, and we'll use the code to see what shape that limit cycle will take.
All right, so here we've got the two pieces that we need. We have our restoring force, negative x, just like we've always had, right? That part has not changed. Here we've got this weird damping force, right? So we've got our mu value. Let's start out with a mu of a half, just to see what that does. Multiplied by 1 minus x squared to factor in how far away we are from equilibrium, times v, or how far away we are from 1, I should say, times v times how fast we are moving. And we're just going to turn off the driving force here. I'm just going to return 0 on that, so we won't have anything coming out for the driving force. And just to investigate what we looked at earlier on the chalkboard, I want to start out near equilibrium. So we're going to start out with 0 velocity and nearly 0 position. So we're going to start at 10 to the minus 4 here. So we got a restoring force, a damping force, driving force. Let's press Control 2 and see what this gets us. The position graph is oscillating like you would probably expect it to. The phase space plot is doing something pretty wild. It's spiraling outward, and for a little bit it looks like it's spiraling out of control, but then eventually it levels out in what I promised was this limit cycle. So we started in the center here. We start spiraling away, right, because the origin, 0, 0, is an unstable equilibrium point. And so we're going to start out there. Here, I'll refresh this. So we're going to start out there at 0, 0, but we get flung away from it, right, because it's unstable. This damping force does not allow us to stay near there. It wants us to get to this weird orbit around here where things start to become stable. You can see this line on the outside starting to become thicker because we're just repeating it over and over again. You can see that up here, we start out at 0, we get flung away from there, but then we end up in this nice kind of stable oscillation. Now, you know by now to expect that's not going to be a nice sine or cosine. And this is definitely not an ellipse, right? It's definitely not even symmetric. I mean, it's symmetric about this diagonal line here, but it's this really distorted shape here. Let's see what happens if we start close to that oscillation there. So let's try a 0 for position and maybe a -2 for velocity. So 0 for position, -2 for velocity. We should be near that sort of equilibrium cycle. And yes, here we get a little bit better look at this. We've got these sort of like shark fins here, because they're curved this way a little bit. And we look down here, yes, we start out really close to our equilibrium cycle, to this limit cycle here, to this pattern that is nice and stable. All right, let's see what happens if we start outside of that. Let's move our position out here, let's say over to 2. So let's increase our position over to 2 now. Control 2 to run. So now we are starting too far away. And so our oscillations actually have to die down a little bit. You can see the little bit here. We started out here. We end up falling into the limit cycle here. Let's start out even farther. Let's move this out to, let's say, 5 on the position axis. And you know what? Let's even make the V move faster. Let's start that out at -3. So we are too far out and too fast to be on that equilibrium path. So we have the initial behavior, but then we get self-corrected to the shark fin pattern. We start out over here. We took a sharp turn here. Here, I'll refresh and focus on the phase space plot. So we start out here. We take a sharp turn. We end up in the limit cycle. So no matter where you start in terms of x and v, you always end up in this limit cycle, in the cycle that you approach as a limit as time goes forward. So what determines the shape of this thing, right? I mean, this is a pretty wild shape here. It turns out the thing that determines that shape is this factor mu. Let me show you what this means. Let's go all the way down to mu equals 0, right? You know what that should do, right? We're turning off the damping. We've just got negative x for our restoring force. That gets you in equilibrium, right? Let's see what happens if we increase this to a 0.2. Control 2. All right, so we started a little too far. That's okay. We end up looping on this. It's almost elliptical. It's like the peak has been shifted to the right. The low point here has been shifted to the left. The rightmost point has been shifted up a little bit. The leftmost point is shifted up a little bit. The rightmost point has been shifted down a little bit. Let's make this go even more extreme. We saw what 0.5 looks like. Let's try 0.75. Excuse me. Now this thing's getting even more distorted, right? Because this point moves over this way, this point moves over this way, this point moves up more, this point moves down more, and we get this start to get this little curvature in here. You see how this is kind of curving in on itself? This is curving outward a little bit. Let's go up to 1. Ooh, definitely took a hard turn there. Remember, what we're interested in the limit cycle. This initial behavior is interesting, but really what we're interested in is the limit cycle. This thing is starting to take on a little bit of a duck shape, right? Let's see what happens if we go past 1. Let's go up to 2. Control 2. Zoom. Yeah, definitely getting some duck shape here. Starting to look like a little rubber duck in there. Let's make it go farther. Let's go, you know what? Let's go all the way to 10. You know what? Let's go past 10 all the way to 11. Oh, and there we go. We get our duck back. Cool. So what I'm going to do now, just to end things here, Control X, Control Paste. We're going to set up a loop around this loop and try out different values of mu. So we are going to go with, for mu in range, or not range, let's do it with a list manually. Let's go 0, and then we'll do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, that ought to be fine. There we go. And now I'll need to indent this. I missed a colon. I will fix that in a second. There we go. And now I need to reset my graphs each round. So we'll cut this part out, put it in here. Put that in there. We'll do this here. Cut that out. Put that in here. Yeah, we'll do the same trick we did last time with the red color. Our red value equals 0. Blue value equals 1. And we'll go with red value plus equals, how many values I got this time? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I could have figured that out just by looking at the endpoints. 1 over 11. 1.0 divided by 11.0. There we go. Now I'll do the same thing here. Copy and paste. I'll get a blue value, and we'll take that to a minus, just so that each of these can have a slightly different color, just so we can tell them apart a little bit better. So this color is going to get replaced by vector red value, 0, blue value. And then we'll do the same thing down here. Copy color equals there. And now what I'll do, I think I will give this one a label, just to say label equals mu equals plus turn into a string the value of mu. That should work out fine. Now, I get comments about this sometimes, because sometimes I need to declare mu as a global, and sometimes I don't. and I'm never sure what the situations are. So I'm just going to err on the side of caution here and add a global. And if you don't like that, then you are better at Python than I am. All right, let's run this and see what happens.
Thanks for watching this series on going beyond simple harmonic motion. I hope it shows you how useful this tool called simple harmonic motion is and what you can do with just a little bit of calculus and a little bit of coding. What we're going to do next on this channel is a series on classical chaos. It'll build directly on this. We'll see a little bit more about the Van der Pol oscillator and other chaotic systems. So I hope you'll watch that and enjoy it. Thanks so much for watching. I'll see you next time. Bye-bye.